let's do a recap of what we have learned about scalar product. The first thing is we learned that if we want to find a scalar product between vector A and vector B, or we call it as A dot B, we can find it using this formula over here, AB cos theta. And because scalar product, the result is a scalar, therefore you can only have magnitude, you have no direction. That's the first thing that we have learned. The second thing that we have learned is if the angle between vector A and vector B is approaching 0, is near 0, then you have greater parallelness. You have greater parallelness, it will result in a greater result of A dot B. Okay, but if your angle between vector A and vector B is near 90 degree or it's more perpendicular, then you have less parallelness. So if you have less parallelness, then your result for A dot B will be less. Okay, so come back to the idea of parallelness. Okay, the third thing that we learned is that scalar product obeys the commutative law. Means by if we take A dot B, we find the scalar product, we will find that it's the same answer as the scalar product of B dot A by changing the order of the two vectors. Okay, so now we have recapped that these are the three things that we learned from the previous videos on scalar product. Let's try to visualize these three things in a more pictorial way. Okay, so let's look at the first thing. If today we have vector A and vector B and we want to find the scalar product, we know that the formula will be AB cos 45 degree. Okay, we have discussed this in the previous video. But what are we actually doing when we are doing AB cos 45 degree? Let's try to rearrange this equation to give it a little bit of meaning. Let's say today I arrange the equation and introduce a bracket. I introduce a bracket to group together the magnitude of A and cos 45 degree. So now A cos 45 degree is in the bracket, and outside the bracket there's the magnitude of B. So now if I group it that way, I'm actually introducing meaning to the equation. Because what's happening in the bracket here is actually resolving the vector A. Why do I say it's resolving? Because there's A cos theta. A cos theta is something that we usually do when we are resolving a vector. Okay, so now let's see where is this A cos 45 degree actually? We know that cos is adjacent. Okay, so it means by we are finding the component of A which is beside 45 degree. Beside 45 degree, that means you are finding the component over here. Okay, if it's sine, then it's opposite, then it's this component. But here we have cos, so it's beside, so this adjacent component. So what are we finding here is A cos 45 degree, which is this component here. I believe you can see that this is actually also carrying the meaning that the A cos 45 degree also carries the meaning that it's the component of A, which is parallel to vector B. This A cos 45 degree here is showing how much of vector A is in parallel with vector B. Okay, so essentially BA cos 45 degree here, what are we doing is we are multiplying B together with the component of A, which is parallel with B. Okay, that's the idea of scalar product. We find for one vector how much of that vector is in parallel to the second vector, and we multiply the two vectors together. That is essentially what scalar product is doing. Okay, so I've visualized to you what is AB cos theta. Now I move on to the second point from just now. We try to study the idea of parallelness. When the angle gets nearer to 0, greater parallelness, greater result for A dot B. So what does that mean on the picture in this diagram over here? Okay, so let's say today you want to decrease the angle of this B. You decrease the angle between A and B. So it means by introduce a new A, you introduce a new vector A to decrease the angle between A and B. So right now I've actually set this to decrease by 10 degree. So here should be 35 degree. So the angle between the new A and B is 35 degree. And we can see if we find the component of the new A, which is parallel to B, how much of the new A is parallel with B, we'll find that the component of A that is parallel to B is longer compared to before. When we decrease the angle, we will find that the component of A, which is parallel to B, is longer now. And if we further decrease the angle, decrease by another 10 degree, I'm keeping the magnitude constant here. This A here has the same magnitude, but I'm decreasing the angle 10 by 10. So right now here is 25 degree. If we find the component of A which is parallel to B, you'll find that it's now even longer than before. Before it's until here, now it's until here, even longer. And if I continue to decrease by 10 degree, then now it's 15 degree. The angle between A and B is 15 degree. I'll see that the component of the new A, which is parallel to B, is even longer than before. Okay, so I'm showing you here, if the component of A, which is parallel to B, is getting longer and longer, of course, if you multiply this longer and longer stuff with B, the answer will be longer and larger. Therefore, greater parallelness will result in greater result for our scalar product. Okay, if we reduce the angle, we are actually increasing the parallelness. So if we are increasing the parallelness, the scalar product will have a larger answer. Okay, so that's point number 2 being visualized on the diagram. Let's move on to point number 3. Point number 3 is the fact that scalar product obeys the commutative law. Okay, so let's try to commute the two vectors that we have here. Okay, let me get back to the original diagram. I remove all the decreasing thing because I'm moving on to point number 3. So let's say right now I commute between A and B. So I put B inside the bracket and I put A outside the bracket. Well, if we just do a calculation, we know that BA cos 45 degree will be the same as AB cos 45 degree, because let's say A is 5, B is 3, then A times B is 5 times 3 equals to 15, B times A is 3 times 5 also equals to 15. We know by calculation that if we move around A and B, you won't change the answer. Okay, but what does that mean in the diagram? Okay, now if we put B inside the bracket, means by we will be resolving B. Just now we are resolving A, now we are resolving B. So if this is the same diagram, resolving B means by we are finding how much of B is parallel to A. Okay, we are breaking B to find how much of B is parallel to A. So in drawing, that would be I break this to find a component of B which is parallel to A. So this is B cos 45 degree. Okay, if you cannot see where's the right angle triangle, yeah, here's the 90 degree. So from here you can know that here's the hypotenuse. Of course, this is angle. Over there will be opposite. Beside will be adjacent. So of course, adjacent is cos. So what we are doing here is we are finding the component of B which is parallel to A. And by finding this component, B cos 45 degree, we multiply it with the magnitude of A. Okay, so based on what commutative law says, multiplying B cos 45 degree with A, the magnitude of A, will generate the same answer as multiplying A cos 45 degree with the magnitude of B. That is what commutative law says. Okay, so what kind of conclusion can you get from here? The conclusion is, it doesn't matter whether we resolve A towards B, we resolve A to find the component parallel to B, or we resolve B to find the component parallel to A. No matter we resolve which one to which one, we will still get the same answer. So in that case, what are we trying to say? We are trying to say that the direction is not relevant here, because the answer of this scalar product has no direction. Therefore, you resolve from which side to which side, there's nothing relevant to it. And that's one of the reasons why scalar product, the answer of a scalar product, has no direction. Which brings us back to point number 1. The result of a scalar product is a scalar and it has no direction. So here are the few things that we have discussed being visualized on the diagram.